Good day, teacher. First, I would like to introduce the team behind this work, which is made up of Laura Bueno, Dayana Castro, Nicole Hernandez, and Sebastian Vega. And today we want to share a protocol that responds a fundamental question, that is, how can we use nanotechnology to solve one of the most urgent environmental problems in Colombia? What you see here on the screen, it's a complete guide to an innovative laboratory, but before we dive into technical details, we need to understand why this matters, right? Imagine this. A nanoparticle is a grain of sand, what a marble is to the earth, right? Its size is extraordinarily small, but the smallness is the greatest strength of these particles. And why are they so important for the environmental remediation? And the response is, first, they have an extraordinary absorption capacity. When we talk about absorption, we refer to ability to capture and retain contaminants in very small amount of nanoparticles, can eliminate a massive amount of contains that conventional method fail to capture. The second, they have a highly reactive. These nanoparticles can participate in chemical reactions that transform hard dose substance into inner or less harmful compounds. And third, this is a crucial, nanoparticle can be refused, especially if we immobilize them in a magnetic hydrogels, as we do here in this laboratory. We can separate them easily with a magnet and use them again, right? In summary, the nanoparticles offer efficient specificity and sustainability in places where conventional technology simply doesn't work. Now, you think what happened in Colombia that makes this laboratory so relevant? And we have a visible and urgent problem with industrial contamination of our waters. The textile industry, especially in cities like Bogota, Medellin, and Cali, generate continuous discharge containing synthesis dyes. These dyes are not merely an aesthetic problem. They literally stain rivers abnormal color, but most concerning is these dyes are highly persistent, poor biodegradable, and many are toxic and mutagenic, right? And what this is the problem with our current system? You think the conventional treatment plants, are even the most modern ones, are not designed to efficiently remove the compounds. They can remove some impurities, but the color and toxic remains is not technological gap we have identified in the national level. This laboratory that we are developing address all these challenges simultaneously is not just science, it's a responsibility to our country, to our rivers, or to our future generation.
The laboratory was divided into four main stages. The first is the synthesis of magnetic nanoparticles, the preparation of the magnetic alginate hydrogel, the dry absorption test, and finally the characterization of the nanoparticles, especially dry diameter. Using two analytic tools, the first is the DLC and IFM. We began the process with two previous preparation solutions. The first solution is the solution A, and contains 0.125 mol iron, chloride hexahydride, solution B is the concentrate 0.125 moles iron chloride tetrahydride. The first magnetic nanoparticular synthesis, using a 100 ml Erlenmeyer flash, we mixed 10 milliliters of solution A with 5 ml of solution B. To this picture, we added 5 ml of sodium hydroxide and manually injected the solution. At this stage, we verified the magnetic properties of the precipitate using a magnet. A washing step followed. The nanoparticles were collected by magnetic separation, and the supernatant was discarded. We added 30 ml of distilled water of resuspend the particles. This washing process was repeated at least 2 times. From the final suspension, 32 ml were collected of DLs and AFM characterization of the magnetic alginate hydrogel. In a 50 ml beaker, we placed 10 ml of 2.5% sodium alginate solution. In a separate 50 ml beaker, we prepared 10 ml of a 6% calcium choice solution. The freshly synthesized magnetic nanoparticulates we are added to the sodium alginate solution, making magnetic steering for 15 meters to ensure homogeneous dispersion. After mixing, we use a Pasteur peptide to drop waste at the nanoparticular alginate solution, into the calcium chloride solution, keeping metal magnetic agitation throughout the process to form hydrogel beds. The hydrogel beds we are left in the calcium and sodium solution for 15 meters. The solution was removed, and the bed we are washed twice with abundant dry dirty water. During the third wash, we added 3 ml of nitric acid. Oil in the red for 15 seconds and rise it throughout it with dished water. This step ashes the ability for carboxylic groups to improve its interaction with cation dry molecules. A final wash which dished water was performed. The hydrogel dress were then drained in the other 30 Celsius for 15 meters, starting a dry average on use. Three part is the absorption test to evaluate absorption performance. We use methylene blue as the model type. In a beaker, we prepared 10 ml of a 1.5 methylene blue solution. Each group was placed in the beaker with 15 ml of the dry solution under Gödel magnetic stirred. Observed reading we are take every 10 meters for a total of 3 measurements. From this data, the percentage of dry absorption at each time interval was calculated. The finality is the part 4, nanoparticular characterization. Finality to determine the hydrodynamic radius. We continued a dynamic like scattering the list analysis. The height and morphology of the nanoparticulate we are evaluating use anatomic for microscopic AFM with the previous college samples.
This is an introduction to different applications of magnetic nanoparticles in industry, the environment, and medicine. These first application to mention are the medical or biological ones. Magnetic nanoparticles are used as contrast agents in MRI because they have super paramagnetism and can be coated with polymeric or ceramic materials to reduce adverse effects in the body, such as inflammation or thrombosis. The magnetita-based nanocomposites are used target drug delivery because they can carry drugs and release them in controlled way. In studies showed that antibiotics, ribosome, doxycycline, and ceftriaxone can attach to magnetita silver nanocomposites. Compatibility magnetita nanovector may weight carboxymethyl cellulose can use deliver drugs to cancer through for followed receptor mediated and endocytosis. They use in hyperthermic therapy because they generate heat onto magnetita films, helping destroy tumor cells with minimal damage to healthy tissue. They can also produce toxic radicals through the phantom reaction, which is used treat inflammatory disease, and they accumulate in effect tissue to throw passive and arctic trigating. Case in not biology application but in the environment or bioremediation. These particles can catalyze in variety of organ reactions, include open epochs, rings, multi-complement reaction, and carbon-carbon coupling reaction, among others. They can also be used as supports for other metals or metals oxide to form hybrid catalytic systems, commonly referred to as metal magnetita structures, thinking about advantage of their modified software and their ability to be easy separated use magnetita fields. nanoparticles are used in environment remediation because they can absorb and remove contaminants for water as efficient nanoabsorbents. Core shell system made of silicon coated magnetita can be functionality to capture chromative and dischromative anions for industrially washed water. In addition, electrochemical technologies for such as electron phantom systems use magnetita modification materials to degrade organic pollution water will simultaneously generating electrical energy.
Okay, the objective of the experiment was to evaluate the absorption capacity of two different amounts of magnetic materials, 3 grams of hydrogel with magnetic and 1.5 grams of magnetic nanoparticles, to remove methylene blue from an aqueous solution initially at 0.5 milligrams per liter. First, the graph shows that the spectrophotometric method at 664 nanometers is highly reliable for quantifying methylene blue in the evaluated range because we have an R-square very close to 1. And then, from the 6 measurements taken, it was observed that both treatments reduced the concentration of the dye, although with slight difference between them. The samples corresponding to 3 grams of hydrogel magnetic showed a final average concentration of 0.446 milligrams per liter, equivalent to an average removal of 10.8%. And on the other hand, the samples treated with 1.5 grams of nanoparticles obtained a final average concentration of 0.454 milligrams per liter, corresponding to a removal of 9.2%. This indicates that under the test condition, increased the absorbent mass slightly improved dye removal, although the difference between the treatments was small. It's important to note that the last sample showed a significantly higher value, reflecting only 2.4% removal. This value could be considered a possible experimental variation associated with factors such as contact time or system homogeneity, incomplete sedimation of absorbent material, or measure error. But if we is clearing this value, the removal of the nanoparticle group would be very similar to that of the hydrogel bit group. And overall, the results suggest that the both systems exhibit comparable absorption capacities with a slight advantage from the large quantity of material. The relatively low efficiency also suggests that experimental variables such as a contact time, mass per volume ratio, or surface activation of the absorbent could be improved to enhance its performance. Thank you so much.